All right. Before we get back into our whole load example, we did a bunch of calculation of Liveload distribution factors last time. I thought I would sort of take a little bit of a break with that and talk about this research presentation that I mentioned earlier in the semester. If you all go back to the schedule, the week before Thanksgiving break, I'm actually not going to be the one lecturing, you all are. What we're going to do is this. Let me zoom into this and I'll sort of pass out hard copies. Now, these are going to be for the bridge engineering folks in the room, not the senior design folks. I actually just get to be spectators for this because they have plenty of presentations they're making this semester, believe me. All right, so here's how this is going to work. What I wanted to do is I wanted to give you all the chance to do a little bit of research on your own and do a presentation on a bridge topic. So what I've decided to do is I want each of you to present on a particular bridge that failed or collapsed. Tell us why, tell us where it is, what happened, you know, what was the impact on the industry and what have you. So here's this. This is just sort of a little handout. Now, we're not doing this for a while, okay? This is the week before Thanksgiving break, so, oh, sorry. So this is, you know, November region and what have you. So there's that. There's that. And then there's that. So it's not like this is going to be a significantly long presentation. This is really meant to sort of just expand your all's knowledge base and, you know, create something different, you know, right before Thanksgiving break, a way where we can all just, I mean, yeah, everybody has their presentation, but I think it might be a way that we can kind of relax and just, you know, sort of sit back and enjoy the ride, as it were. Now, so you're going to prepare a short PowerPoint presentation. I mean, I've got 12 bridge engineering students in here, so it's only going to be about 10 minutes apiece, you know, and then I might ask a question or two, and then we'll move on to the next one. We'll just keep going, and that'll be the week before Thanksgiving break. So tell me, so the presentation should include a description of the bridge itself. Tell us what you're presenting on. Tell us what happened. What was the cause of the bridge failure? Were there any investigations, any research on the topic, anything that was learned about the particular event? Was there any impact on bridge engineering practice? Did we learn stuff from this particular bridge failure and it then cause us to change the way that we design bridges in the future? And make sure your final slide has sources and citations and things like that. So far, so good? All right, now, as for what bridge do you research? What bridge do you present on? Well, it's funny how I have 12 different bridges in here. You all are going to be picking your bridge. All right. So let's walk down the line. Pick one. Pick one. I've got American bridges. I've got international bridges. Stuff that's recent, stuff that happened a while ago. So let's see what happens. I think I've got one in Canada, one in Portugal, one in Vietnam. So there we go. All right. Oh, no, there's still a few left. And it's still pretty random because you don't know what was already selected. So. Yep. I left your name out for some reason. I'm just kidding. All right. Okay. All right. So one student wasn't able to make it, so they're going to be doing theirs on the Hone Bridge in 2000. All right, so let's just sort of see what do we got going on. What do you got? Okay, so you got the Tennessee Hatchie River Bridge. You've got the cont'd Bridge. That's a Vietnamese structure. You've got Mianus River out in Delaware. You've got St. Aubrey Cousins. That's a Canadian structure. You have, oh, I-35. And you've got, oh, Colorado, that overpass. That's an interesting one. All right. Oh, you got the Silver Bridge. The Mothman did not bring down the bridge, regardless of what Dr. Nichols says. Hensey-Ribeiro disaster. What do we got? I'm just curious. Okay, so Skagit River, we got Cont'd Bridge, and we've got Yellow Mill Pond. Okay, so I was just curious just to see if everybody, well, regardless of if you got what you want, that's your bridge. So you've got every one of you has an individual structure that experienced some type of failure. It's your job to research that failure, tell us what happened, why it happened, any impacts, whole 9 yards. Again, the day before Thanksgiving break, just 10 minutes apiece. We'll ask a couple questions. You all still got to show up, and oh yeah, and that's pretty much all there is to it. So again, this is not due anytime soon, November 15th, so you got plenty of time, okay? Sound good? Any questions? All right. Okay. All right, now I've got a couple handouts for you today. We might get to some of this today, we might not. It just depends. My number one concern and priority today is to get through all this load stuff, at least so that you all can successfully negotiate your homework, your homework this week. Okay. Now, hopefully, you all have at least started on that homework and gotten some headway. I mean, you can't do all of it right now, but you should at least be able to do a significant component of it. All right. And there's that. So that's Appendix D. We're going to spend a lot of time in Section 6 of the spec later, because Section 6 is the section that deals with steel structures. And that section has a number of appendices in the back. And Appendix D is sort of, I guess, a good place to start in terms of looking at the resistance of steel girders, because there's a lot of fundamental calcs that are reviewed in Appendix D, and that's kind of where we're going to start. So I got, let's see, 3 here, and then 4 here, 1 here, and then 5 there, 2 here, and 1 there. Okay, so everybody should have an Appendix D. You should have the slide packet, which will come after our load stuff, and you bridge engineering folks should have a bridge and a handout on this. All right, everybody good? Okay. All right, so where were we? Okay, so I'm not going to get too in-depth with this presentation since we've kind of already talked about it, but let's be clear where we're at and where we're headed. So we've been spending the last little while in the course talking about loads on bridges. So we talked about dead loads, we've talked about live loads, and we had a homework where you all took a given structure and then determined its dead load characteristics. Now we're looking at live loads. So live loads, there's really 2 sort of problems that we need to assess. We need to determine where to place these live load components longitudinally, and that's where we use an influence line. We also need to determine where we place these elements transversely, and that's where live load distribution factors come into play. Now, we've gone through and kind of reasonably explained what a live load distribution factor is. You basically take the results of a line girder analysis, or a line girder analysis being what you all learned in Structural Analysis 1, or wherever you took structural analysis, shear diagrams, moment diagrams, stuff like that. You take your fundamental line girder analysis results, and you then adjust those results by an appropriate distribution factor, and then that's supposed to represent, that product would then represent the, quote, real life moments on the structure. Of course, there's a little bit of approximation in that, but by and large, they're pretty good, okay? And, excuse me. So as you know, I mean, I'm not going to go into the history and whatnot because you all are pretty well versed on that. But the idea behind distribution factors is that there is a large suite of these things dependent upon the particular type of structure and force effect that you're looking at. So They're discretized based on whether you're looking at slab-on-beam steel bridges, whether you're looking at box bridges, reinforced concrete T-beam bridges, what have you. Based on all these given structures, you've got distribution factors for moment, distribution factors for shear, interior girder distribution, exterior girder distribution, single lane loading scenarios, multiple lane loading scenarios. You know the drill. So instead of belaboring everything going on here, let me get to the notes. So here's our section on Liveload distribution. Blow that up a little bit. So this is what we did last time, and we spent a fair amount of time going through this. So we looked at how do we compute the longitudinal stiffness parameter, and we get that from the section properties of the non-composite section and the modular ratio. Went through and computed that, and then we were rocking and rolling with our distribution factors. We had interior girder moment taken care of, interior girder shear taken care of. We did the lever rule analysis. We've got exterior girder moment taken care of, and exterior girder shear taken care of. And there was one, at least, large chunk of computations that were left, and that was special analysis, and that's where we stopped. So before I, move on, does anybody have any questions about where we're at? Everybody, am I okay to just sort of pick up and keep moving? Everybody good? Okay. Keep in mind, a lot of this you should be able to quote-unquote Excelify. You should, based on some pretty basic input, Excel can compute a lot of this for you. I'll leave you all to the organizational, aspects of it. But the nice thing about Excel is that based on input, you should be able to compute any output with enough time and room on your spreadsheet. So what I'm going to do, I'm going to erase this where it's special analysis to be continued because it's being continued right now. So special analysis. Oh, what happened there? Okay, so if you don't have it out, it's probably a good idea. What the heck? My pen's going in and out. Let's see. Yeah, it's running out of ink. It's a good one. Okay, all right. So we're going to go through and conduct this special analysis procedure. The first thing we need to do is figure out how many times we're going to conduct special analysis. Now, we do that based on the width of the roadway, okay? So let's start off with that, okay? What is the width of the road or roadway? 34 feet, okay? Now, the width of a design lane is 12 feet, okay? So if I take 34 feet over 12 feet, that's what? .83. So let's see if you all remember. How many times would we then perform special analysis? No. 2. We only put as many design lanes as will fit on the structure. So we're only putting 2. Okay, so we performed special analysis twice. So maybe I'll put 2 cases. If that makes any sense. 2 cases of special analysis. Okay. My pen is not happy with me right now. Okay. All right. So for special analysis, if you recall, we've got a number of things we need to figure out. So I'm going to start listing some parameters, and let's see what we can come up with. To start off, we need to determine NB. My goodness. Hold on, give me 1 second. Let me try something real quick. I was told that if my pen goes out and it decides to be funky, that I should unplug and plug this monitor back up. Let's see what's going on here. Okay, that made it worse. Now it's not working at all. Oh, don't tell me. No, it's not that. It's the hardware. Although we have had to do that before. Oh, there we go. Okay, for some reason I feel like it's working a little bit. Okay, NB. Okay, so NB is simply the number of beams which equals what? 4. There's 4 beams on this bridge. Okay. All right. So next thing we need to determine is this exterior distance x. And what that is the distance from the center of gravity of, let's put a little decimal there, of the, how should I put that? We'll say the pattern of girders. To the exterior girder. In other words, if I have a bridge that looks something like this, all right, and I have, I'll make it up. Let's say, I got a whole bunch of beams. 1, 2, 3, 4, 5, 6 beams, okay? This exterior distance is the distance from the center of gravity of the pattern of girders to the exterior most girder. So that would be x ext. Okay? So help me out. For our pattern of girders, what would that be? The center line web, yes, center line web. $15.7. Well, think about, go back to this bridge, okay? How many beams are there? 4. And how far are they spaced apart? 10 feet. So think about outside to outside. That would be what, 30? So what's from the center to the edge? 15. Make sense? So 15 feet. Not too bad, right? That's simple. Okay. Now, this next part is what I'm going to call the, let me scroll down a little bit. This next part I'm going to call the x distances. And the closest analogy I can think of is we're going to kind of find an effective moment of inertia of all of the girders, okay? So here's how this is going to work, okay? So how many girders do I have? 4? Okay, so let's draw a little table. Girder, we're going to say 1, 2, 3, 4, okay? Now, what we're going to do is this, okay? Let me sort of draw a little picture here to kind of illustrate what's going on. Okay, so I've got 1, 2, 3, 4. Okay, now I'm going to measure all of these distances from the center of gravity of these girders, which is essentially right here. So in other words, this is, I guess, x bar. Make sense? Everybody good with this? So let me ask you a question, all right? How far is it, and let's number these. Let's go through and number these. So we'll say this is girder 1, this is girder 2, this is girder 3, and this is girder 4. Okay? How far is it from the center of gravity, that centroid, if you will, to girder 1, to the center line of girder 1? 15. Now, he said minus 15. I'm going to go ahead and put minus 15, but it's not going to matter, all right? Because ultimately, what we're going to do is calculate x squared. So negative times a negative is a positive, just as positive times a positive. All right? So help me out. from the center line to girder 2, what is it? 5 or negative 5, it doesn't really matter. And then what do we have? 3 is 5 and then 15. Make sense? So maybe we got negative 5, 5, 15. So 15 times 15, that's 225. So this is 25, 25, 225. Sum those up, what do you get? You get 500, right? So I propose that the sum of over the number of beams of x squared is 500 square feet. That's not too bad, right? Everybody okay with this? See, I just want to go back. I do want to go back to the PowerPoint real quick just so that everybody's aware of what we're doing. So here's the formula for special analysis. So we've already got the number of beams. We've already got this, this centroidal distance, if you will, to that exterior girder. We've already got this denominator. So this isn't that bad, okay? I know it looks like a really funky formula, but it's pretty simple, okay? Again, kind of the same thing as trying to determine reactions on pile groups. Basically the same idea, okay? So the next thing we've got to deal with is this number of lanes and then this centroidal distance. I actually just noticed I have a mistake. I'm sorry. This is right here. Actually, let me enable editing so that you all see what I'm talking about. Come on. This right here, that's supposed to be NL. Apologies for that. This is on slide. Ooh, I don't have slide numbers on here. I'm sorry. It's on the Liveload distribution factor slide, and it's on slide 17. So that's probably third one from the end. All right. That's supposed to be NL. I apologize about that. That actually is somewhat important because it clarifies what I'm about to mention now. So sorry about that. Whoops. Did everybody find that? I'm sorry about that. Okay. Here was the point I was making, so this is why this is valid. The number of beams doesn't change each time you do structural analysis. It's still 4 beams. This external center of gravity distance, it doesn't change. It's still 15 feet. This dimension, or this quantity, doesn't change either. That's essentially a moment of inertia of the girders, an effective one, if you will. That's going to be 500 square feet. What is going to change is the number of lanes and then this eccentricity distance. So to give you kind of an idea, when we do special analysis for the first case, we're going to assume 1 lane loaded, so this is going to be 1. When we do it for the second case, we're going to assume both lanes loaded, and this is going to be 2. So if you had to do, special analysis, 8 times, you would do it with NL of 1, and then NL of 2, NL of 3, NL of 4, NL of 5, and just keep doing it, okay? Make sense? All right. What's up? We haven't done it. Well, no, the 34 yeah. What if you only had 2 lanes, 10 foot, with huge shoulders? There's still only 2 lanes, but that would work out for 3. Still do it 3 times. Do it 3. Yep. I don't care what the paint on the road is. And it's a good point. There is a big difference between a traffic lane and a structural design lane. And it's very common that a structural engineer might say that there's 4 lanes, and a traffic engineer might say, well, there's only 3 lanes. That's fine. And from a bridge designer's perspective, we don't care about the paint on the road. All right, that's a good point to make. Everybody okay on that? So yeah, there is a big difference between a transportation engineer's traffic lanes and a structural engineer's design lanes. We don't care. All right, so far so good? All right. So we're going to conduct special analysis twice, so we'll do it once with an NL of 1 and second one with NL of 2. Let's see how we would do that, okay? I'm going to do my best to try and be artistic with this because I got to be somewhat artistic in my my diagrams. Okay. All right. So let's look at our E distances. Now, these E distances are basically the truck eccentricities. So I'll say it, truck eccentricities. Okay. So what do I mean by that? Okay. So let's see. So bear with me. I'm going to do my best to be artistic. Okay. So here's this. All right. So what do we got? We've got a girder that's about, I don't know, right here. We've got a girder that's about right here. And then we've got this line right here, which is what I'm going to call that X bar distance. All right. So far, so good? Everybody good? Okay, now let's go back to what the lever rule stated. The lever rule stated that here's my edge of the barrier, right here. I go 2 foot over, right? 2 foot over, and then my truck goes there, right? Remember that? So 2 foot from the edge of that barrier. So I put, you know, one wheel right here, and then another one about right here. So this is what I'll say. This is truck 1. Right? Make sense? And this was 0.5. This was 0.5. So far, so good? All right, so let's put some dimensions on here. So this dimension here, from here to here, this was what, 2 feet? What was this dimension right here? How wide is that barrier? One foot 6 inches, so that's 1.5 feet, right? Make sense? All right. This dimension here, all right. 3 foot 6, so it's 3 foot 6, so it's actually 3.5 because that's half a foot, right? And then this is 10 feet. And then what's this dimension right here? 5 feet. Okay. So far, so good? Now, would you believe me if I said that, okay, I've got this truck right here, you know, 0.5 and 0.5, where this dimension here, I'm going to scoot this up a little bit. Bear with me. So this is 0.5. This is truck 1. And this dimension here, this is the width of the truck, right? So this is 6 feet, right? That's how wide the truck is, all right? Would you believe me if I said that the centroid of that truck is about right here? Somewhere about like that. So what is this dimension? 3 feet. So far, so good? Okay. My question to you is this. How far is it from the centroid of that truck to the centroid of the whole thing? What is this dimension? Say it again? 12 feet. Exactly. This dimension is that first eccentricity. Does that make sense? These eccentricities are the distance from the centroid of the pattern of girders to the centroid of a given truck. Okay? Now, where does the next truck go? I have truck 2. I can't put it right on top of that truck. Well, it goes back to our design lanes. How wide is a given design lane? No, well, that's the width of the whole road. How wide is a lane? 12 feet. Okay? So this truck occupies a lane that is 12 foot wide, right? So the next truck needs to probably go somewhere over here. And it probably is going to go over like that a little bit, where this distance is 6 feet. There you go. I was getting ready to ask that. If you look at the dimensions, you'll find that the center of this second truck and the center of gravity of the whole thing just happen to coincide, right? So, you know, in other words, this is truck 2. Oh. All right, so this is truck 2. And it just so happens that the center of gravity of the truck and the center of gravity of the pattern of girders happens to coincide. So I propose to you that if the first eccentricity is 12 feet, the second eccentricity is 0. Just this one. Just this one. I mean, we had some very special circumstances here. Like, watch this. I mean, we had some very special circumstances. We had an overhang that was 3.5 feet. We had a barrier width that was 1.5 feet. So that 2-foot eccentricity put that first wheel load right there. That was just luck of the draw, okay? And then the dimensions were such that with the width of the truck and the girder spacing, it just so happened to be right there. Not always the case, but just happened to be for this one. Does that make sense? Everybody okay with this? So is everybody okay with E sub 1 being 12 feet and E sub 2 being 0? Everybody good? Okay, all right. So, show you how this works. It's pretty simple. All right? So, I want to get myself a little bit of room. So, let's finally do our special analysis. All right? So, how many times are we going to do special analysis? Twice. So let's look at our first case of special analysis. Okay, so the number of lanes is going to be 1. And then what do we know? Okay, we need to determine the sum of all of those eccentricities. Well, since we're only dealing with one truck on the bridge, it's just going to be E1, which happens to be 12 feet. Okay? If we were doing it twice, if we were doing case 2, it'd be E1 plus E2. If we had to do special analysis 4 times, we'd do E1, E1 plus E2, E1 plus E2 plus E3, and then E1 plus E2 plus E3 plus E4. We just keep cumulatively adding up those trucks. Make sense? Everybody okay with that? So I propose then that special analysis for one lane is going to equal the number of lanes divided by the number of beams plus x ext times the sum of all my eccentricities divided by the sum of my x squared. So that is 1 over 4 plus what? What is that? 15 feet times 12 feet over 500 square feet. And that comes out to be what? .61. Now, is that my distribution factor? The answer is no. Because if you recall, remember those whole multiple presence factors? Remember when we did the lever rule, we had to take the lever rule and adjust it by that multi-presence factor? Because multi-presence factors, they're built into all those nice, pretty plug-and-chug equations, but they're not built into methods like this. So we have to go out of our way to incorporate it. So let's see if you all remember. What's the multi-presence factor for one lane loaded? We used it for the lever rule. We took the lever rule analysis and then we multiplied it by something. What were you saying, Mr. Yukonek? It was 1.2. This is a good first guess. Oh, wrong one. All right, so if you recall, they're right here. So multi-presence factors, they're in that section 3 of the spec. So if you've got one lane loaded scenarios, you multiply your distribution factors by 1.2. If you're dealing with 2 lane loaded scenarios, it's 1. 3, it starts dropping down. And anything greater than 3, 4 lanes, 5 lanes, 6 lanes, you just cap it off at 0.65. All right, make sense? Everybody good? Okay. So let me go back here, extend this down a little bit. So here's my reaction from special analysis, the distribution factor, which maybe I should clarify. This is, here, I'll write this afterwards. Let's just go ahead and calculate the distribution factor. It's 1.2 times 0.61, and that is what? .73, and we'll say what, 732? Yeah. Okay, all right. Let's clarify what this is for, okay? This is for exterior girders. This is for moment and shear. And it's for how many lanes loaded? 1. It's just 1 lane loaded scenarios because it's a special analysis considering only 1 truck. So 1 lane loaded. Okay. So that's case 1. Any questions? Now let's do it again for case 2. So what do we have? We have, in this case, we have 2 lanes loaded. We have the sum of all of our eccentricities being E1 plus E2, which just so happens to be 12 feet as well, right? So in this case, I propose that R2 would then be 2 over 4 plus 15 feet times 12 feet divided by 500 foot squared. And that comes out to be, this comes out to be 1.1? I got 0.86. Yeah. Because think the difference between the first one and the second one is we're only adding 1/4. So if you take that first one and add 0.25, that's what you should get. Sound good? All right, now, is that our distribution factor? Well, we take our distribution factor, or I'm getting ahead of myself. We compute our distribution factor by taking this and multiplying it times the appropriate multi-presence factor. What is the appropriate multi-presence factor? 1. So in this case, it comes out to be 0.86. Make sense? Any questions? Now, from a design standpoint, let's sort of summarize. So we've got this massive list of distribution factors, right? Massive list of distribution factors. This is what I like to do in terms of design. I don't really think it's worth it in most cases, to design the girders independently. In other words, let's just pick the worst case distribution factor from interior girders and exterior girders, and let's just design them all the same. So let's do this, okay? So I'll say summary. Now, I'm going to say summary, but I'm going to indicate that this is only for strength and service limit states. Because when we do fatigue limit states, we have to handle it a little differently. It's not complicated, but it's pretty straightforward. So help me out, all right? The distribution factor for moment and the distribution factor for shear. Now, you all go through your notes and scroll up, and you tell me what was the absolute largest, worst case moment distribution factor that we computed out of everything that we did. .8, okay, so we've got 0.84. Is there anything higher? Okay, no, okay, all right, 0.952. What was that for? That's for shear, okay? What's that? Okay, the shear one. That's what he's talking about. Yeah, that, okay, and I'll go ahead and tell you, that is the largest one that we computed for shear. And it was what, interior girder, like 2 lanes loaded? Is that what it was? Interior girder. So we can say, let's go ahead and indicate that. Interior girder, I'll say, multiple lane loading, because it's 2 or more. Now, for moment, you said 0.84. I think there's something a little larger. Hint, it's up there right now. 0.86. The 0.86, the 2 lane loaded scenario that we got from special analysis. Remember, those are for moment and for shear. So I propose it's 0.86. And where did we get that? We got that from special analysis. We'll say special analysis for 2 lanes loaded. So far, so good? Not too bad, right? Okay, now, we're not quite finished yet because we've got a little quandary with these values. Everything that we've computed, or at least most of what we computed, actually, no, it's not even most, it's a very small amount. But let me say this, all I can state definitively is that these are the governing distribution factors for the positive bending region. Okay? Why can I only state that, why can I only make that claim for positive bending? Because earlier, what was the very first thing that we computed? Very first thing in all this. kg, we computed this. Let me scroll up. We did a lot. This. Remember, the first thing that we computed was this term kg. Okay? We used kg in some of our distribution factors. Okay? So, because of that, we've got to go back and compute the negative bending distribution factors that are appropriate. Now, relax, we're not going to do all of them. Okay? We're not going to go back and do every single distribution factor all over again. Because, for instance, let's take the lever rule. Does the lever rule really change whether or not you're in the positive bending region or the negative bending region? No. The only difference between the positive bending region and the negative bending region is the girder size is a little different. A little bit of a thicker flange. That doesn't change the girder spacing or anything like that. So we don't have to go through and do the lever rule again. We don't have to go through and do special analysis again. We actually don't even need to go through and compute any of our shear distribution factors. If you scroll down, let's look at the shear distribution factors. The shear distribution factors, for instance, for the interior girder, they were only a function of girder spacing, right? And for the exterior girder, they either came from the lever rule, special analysis, or from this modification factor. And that's just a distance from the exterior girder to that curb. So I propose that this shear distribution factor, right off the bat, I know that that's going to work across the board, the 0.952. I propose that that's going to work across the board. Okay? Sound good? Okay. So all we got to do is moment. So let me extend this out a little bit. Okay? So let's go look at negative bending. Negative bending. Okay. So let's look at our longitudinal stiffness parameter. So kg. So we have we're going to need a few things. We're going to need our modular ratio, which what's that? 8. That doesn't change. We're going to need I. We're going to need A. We're going to need EG. So let me go back to my folder. Let's go back to my notes. Section properties. Let's go here. And let's look at our negative bending region. So here's my spreadsheet with the negative bending region properties on it. And we're interested in this one right here, right? We're interested in this one. So let me screen capture this. Oh, there we go. Make that a little smaller. I think that's good enough. Okay, so these are the section properties from the negative bending region. If you can't read that, I'll go ahead and fill this in. So the moment of inertia was 19,615 inches to the fourth. The area was 56.75. So 19,615 inches to the fourth, and the area was 56.75 inches squared. Okay. All right. Now EG, let's see if y'all remember that. Remember EG was the distance from the center of the beam to the center of the slab. Okay, so let's get to the center of the slab first. Okay, so I need to, let's see if we remember this. Okay, so we start at the bottom, go bottom flange thickness, right? Web depth, haunch, half the slab thickness, and then we subtract the centroid, right? So help me out with the dimensions. Make sure y'all paying attention. What's the bottom flange thickness? In that negative bending region. Remember, right there around the pier. That middle support on that beam. 1.25 inches, so 1.25 inches. All right. Plus the web depth, which is 42 inches. Plus the haunch, which is 2 inches. Plus the slab thickness, which is half of what? 8. Not 8.5, 8. Because remember, we're using that structural slab thickness. Okay, minus the centroid, which I propose that that is 20.613 inches. And how am I getting that? That comes from right here, that bottom of steel. You know, from the bottom of the section to the centroid, or from the centroid to the bottom, either way you want to look at it, that's that 20.613. If you want, we can just take that divided by that, however you want to do it. All right, and plug and chug, what does that give you? Say it again. 28.637. All right. So if that's the case, and that's inches. So if that's the case, then kg is the modular ratio times I plus AEG squared. And we've already done a calculation like this before, so I'm going to let you all plug and chug and tell me what you get. I'm breaking the table. It'll be all right. Anybody getting an answer? Just nearest whole number. And remember, don't forget to square the EG, or E sub G. Say it again. Anybody else getting that? Okay, all right. So, oh goodness, got caught on there. Okay, so we've got a new KG, and this is slightly different than the one we dealt with last time. It's slightly higher. It's not terribly higher, but we might as well go through and do our calcs. Now, we only have to go through and check 3 distribution factors. Okay, we only have to check 3. All right, so what are those 3? We have the interior girder moment ones. Now let's see if we can remember these. Let's recall that S is 10 feet. Let's recall that L is 90 feet, the span length. TS is 8 inches. All right, let's see how my memory works. We have the 1 lane loaded, and then we have the 2 lane loaded. Did I get that right? What's that? Did I get that one right? I think that's right. Okay, so somebody who's quick with the calculator, I know this is a convoluted one. Let's see if we can get a couple answers. We'll do the first one, then the second one. So this is a tough one, or not a tough one, just a long one. This is the easy part for me. Nobody's laughing. Goodness. You're a tough crowd. .417, and this. Well, hold on. Let me see something. All right, the first one. What do we get for the first one? Okay, we got. Oh goodness. When we did this the first time, we got .508, and the only thing that changed is this number got slightly larger. So the number shouldn't have gone down. So. The numbers should be probably. Okay, but the same thing. When we did it last time, we got .508, and the only difference between this and what we did before is this number went up. Is there an exponent? Like, check your exponents. This would be .4, .3, and .1. Okay. That seems a little high. 510. That actually sounds pretty good. Is anybody else getting 0.510? You didn't bring a calculator, did you? Oh, do the second one. Okay, 0.510, that sounds right, because look at the numbers. Like if I took this one and just slightly increased it, it's going to only slightly bump that up a little bit. So 0.51. The next one, I'm guessing like 0.74 or something. So 0.737. Is anybody else getting that? I know these are involved. They're not hard. It's just a lot of plug and chug. Anybody else? What do you got? You got? Hold on. We'll do it together real quick. Let me throw it on Excel. So, all right. So, we'll look at that later. All right. So what do we have? We have, let's do that second one, 0.075 plus we have 10 divided by 9.5 raised to the 0.6 times 10 divided by 90. Oh. I was working on it. Let's do that. All right. That is raised to the 0.2. And then multiply another big thing raised to the 0.1. And that is the kg. What was kg again? 5,29235 divided by a quantity. And that quantity was 12 times L, which is 90, times 8 cubed, right? Again, I just sort of go crazy with the parentheses just to be sure. Oh. So let me hit enter. And that's what I'm getting, 0.737. All right, and you see the formula up there. Everybody okay with that? Oh, not that. Everybody okay with that? All right, so make sure you're clear on how to do stuff, that stuff. All right, so, okay. Okay, the only other one that we have to do is exterior girder moment. No. Sorry. Exterior. Interior girder. Wait, no. We need to do exterior girder moment, 2 lanes or multiple lanes loaded. Sorry. I'm in need of coffee is what it is. Okay. So if you recall, this is where we take that distribution factor for the exterior girder, and the way we compute it is we take the distribution factor for the interior girder and modify it by that value E. Remember that? Everybody remember that? So what was E for moment? What was that? It's going to be like way up here. Remember this? That 0.77 plus DE over 9.1. Remember that? And DE was measured to be 2 feet from the exterior girder to the curb. So I take the worst case scenario, which is 0.737. I then multiply it by 0.77 plus DE over 9.1, which is 0.737 times 0.77 plus 2 over 9.1, which is what? Zero point seven what? 729. 0.729. Okay. Now, unfortunately, you're going to be mad at me because you'll see here in a second that this was actually, now that we've done this, kind of a pointless exercise because all of these distribution factors are distribution factors for moment, okay, for moment. All right, 0.51, 0.737, 0.729, all for moment. But none of them are bigger than this 0.86. None of them are bigger than that. So I propose that a summary the distribution factor for moment is again 0.860 and the distribution factor for shear is 0.952. And these also work in negative bending regions. Okay. Also, again, this is only for strength and service limit states. Okay? We're going to do the fatigue distribution factors now, although we're not going to use them, but they're very simple. They're very simple. All right, everybody good? Okay. All right. So fatigue. Here's how fatigue works. When you do a fatigue limit state assessment, you are doing it based on a single truck. Just one truck, okay? So the first thing that we're going to do is let's do moment, okay? Let's do moment. Let's go through and pick out the largest moment distribution factor, but one lane loaded, one lane loaded. So let's scroll up to the very beginning. Let's just sort of scroll, okay? So what do I have? All right, so I'm at the very beginning. Let's think, moment, one lane loaded. So, okay, so interior girder moment, I got what, 0.508, right? I'm not looking at the next one because that's multiple lanes loaded. So 0.508, we're looking at moment. 0.84, right? Distribution factor, exterior girder, one lane loaded. Special analysis, what was that 0.732? Right? And that's probably it, right? 0.51. So the largest one we got was 0.84, right? That's the largest one for one lane loaded. I propose that for the fatigue limit state, and if you want, you can say a fatigue distribution factor for moment is the largest one lane loaded regular distribution factor divided by 1.2. And why am I dividing it by 1.2? Because I got to take out that effect of multiple presence. We're only looking at a single truck, okay? So for distribution factors for moment, the largest one we got was 0.84. Take that, or 0.840, divide that by 1.2, and that comes out to be what? 0.7. 0.7. All right. For shear, same deal. The fatigue distribution factor for shear is the largest one lane loaded distribution factor for shear divided by 1.2. So it's some value divided by 1.2. What is that? Okay, let's do the same thing. Start at the very top. Let's see if I missed something. So moment, shear, well, we got 0.76. .84, probably 0.84. There we go, 0.84. So why did they happen to be the same? Because that largest factor came from the lever rule. So far, so good? I got one last calc and we'll take a break, all right? One last calc. We've done distribution factors for moments. We've done distribution factors for shears. What about distribution factors for deflections? It's very simple. This is specifically for live load deflections. The live load deflection distribution factor, okay? What's the, hold on, let's do this. What's the maximum number of lanes? 2, okay? And for 2 lanes, what's the appropriate multi-presence factor? 1, okay? What is the number of beams? 4. I propose that we assume for live load deflections that everything deflects equally, so we just take 1 times 2 trucks over 4 girders. And that's it. And that's it. Everybody good? It's not too bad, right? There's no super duper fancy formula for live load deflections because it's not a prescriptive check. It's an optional live load deflection check, so that's basically it. Any questions? All right, let's take a break. What we're going to do when we come back, we're going to utilize these distribution factors real quick, and we're going to combine moments and shears to actually get factored moment envelopes that we can use for design. If you all have had concrete design or steel design, remember that whole, phi mn has to be greater than or equal to mu? What we're going to look at here in a second is mu. How do we calculate the factored moments? We'll then spend the rest big chunk looking at how do we calculate phi mn. If you understand phi mn, you understand mu, we can start designing. All right. That's all I got for right now. Let's pick it up. What time is it now? It's 7:40. You all were troopers, so how does like 7:55 sound? Sound good? All right. 7:55. Give y'all 15 minutes.